Okay, folks, we are starting a brand new chapter today. The type of concept that we're talking about is going to be around heat. So how does heat involve itself with chemical reactions? How do we describe it in a chemical way? That's what chapter 5 is all about, and it's thermodynamics. So to get to the basics, thermodynamics is the study of energy and its transformations when we talk about heat in this chapter, I want you guys to think about heat on a molecular level. So when molecules are hot, they move faster. When molecules are cold, they move slower. So we're talking about the kinetic energy, which is the energy of motion of particles. Okay, so if you haven't gotten a refresher on that, kinetic energy is the energy of motion. And so when we're talking about heat, we're talking about, are the particles moving fast? Are they moving slow? If you take physics, you're going to talk about heat in terms of the transfer of kinetic energy. But for chemistry purposes, we're just going to talk about just the basic kinetic energy of the particles involved. Next is temperature. So there is a difference between heat and temperature. So heat is literally just the kinetic energy of the particles. Temperature is a measurement of that heat energy. And specifically, if you want to get down to the specifics, it's an average of the kinetic energy of all the particles. If this second definition doesn't make a whole lot of sense to you, don't worry. We're going to talk more about what average kinetic energy means in our gas law chapter. So when it comes to how we describe heat, it's important to understand heat is always being transferred from one place to another. So I want you guys to look at this first example. We've got an ice cube, and it is in the process of melting right now. So I want you guys to think really quick. In terms of this ice cube, is heat, as it's melting, is heat entering the ice cube or is it leaving the ice cube? So if you think about it, heat should be entering the ice cube if the ice cube is melting. So we have our heat entering. Okay, so in this case, what we're examining is the system. The thing that we're looking at is the ice cube. And then the surroundings is literally everything else in the universe except for the ice cube. So the universe minus the ice cube. So that's literally the air around the ice cube, the table that it's sitting on, the planet that the table is on. Literally everything else is the surroundings. And so in this example, if you guys notice, heat is entering the system. Okay, the system being the ice cube. If heat is entering the system, we would call that a change in heat that is positive, which is endothermic. Okay, so the overall system is gaining heat energy. So that if you guys ever see this triangle in science means delta, which means change in. So a change in heat in this particular example is positive because we're gaining more heat energy. So our change in heat energy is positive. We are gaining heat energy that makes it endothermic. It's nice to make that correlation endothermic. So like enter, heat is entering. Okay. Meanwhile, take a look over here. We have a cup of coffee that is cooling on a table. Okay, so we've got some steam escaping our cup of coffee. So in this case, we're looking at the coffee cup, or the coffee itself, I guess we should say. And then the surroundings would be everything except for the coffee. So the universe minus the coffee. Okay, so if we are just looking at the coffee and the coffee has been made and is now sitting out on a table, is heat going to be entering this coffee or is it going to be leaving the coffee? Think about it. and heat should be leaving the coffee because the coffee is going to be really hot. The air is not going to be as hot, so heat is going to be leaving the coffee. We all know if we have a hot beverage and we leave it out, it'll eventually cool down. And that's the idea, is that heat leaves hot objects and enters colder ones. So in this case, we would call this a change in heat energy that was negative. And whenever you have a change in heat energy that is negative, you call that exothermic. Okay, in this case, you have heat exiting the system. Okay, so our change in heat energy was negative because the amount of heat that's in the system is going down as it's escaping the system. So we have positive changes in energy and negative changes in energy. If you're losing heat, you're exothermic. If you're gaining heat, you're endothermic. Okay, so this all relates to the concept of the first law of thermodynamics, which states that energy cannot be created or destroyed. Okay, which means the amount of heat energy in the universe is constant. Okay, so if I, like for this example, if I took the energy that was contained in the ice cube and I added it to the energy that was remaining after I took the energy of the ice cube out, I would get the same amount of energy. So it would be absolutely constant. Sorry guys, there's a spider crawling around in my room right now. I have to kill it. Hold on 1 second. Oh, okay. Oh, okay. All right. Spider's dead. All right. Sorry, guys. Okay. So anyway, yes, this relates to the fact if you added the heat of the surroundings plus the heat of the system, you would get a consistent number. We don't know what that number is because it's impossible to quantify the amount of energy in the universe. But we know that if you add the system plus the surroundings, you'll get the same number every time. Basically what that boils down to is that whatever the system releases is exactly what the surrounding gains, and whatever the surrounding loses is what the system gains. Those numbers has to match. Again, back to the concept of kinetic energy. Again, kinetic energy is the energy of motion. Okay, and in this case, again, we're talking about the motion of particles on the molecular level for chemistry. And then if you ever need it, kinetic energy, the formula for kinetic energy, and physics people, you might know this already, is 1/2 mass times velocity squared. Okay, mass is the m measured in kilograms, and then velocity is meters per second. Okay, you're never going to have to use this formula in chemistry class, but it does come up in physics. So if you ever take a physics class, now you know the formula for kinetic energy, 1/2 mass times velocity squared. We already covered what temperature is, so I'm going to cross that one out. And then whenever I talk about kinetic energy, I like to clarify what potential energy is. I want to remind you guys that potential energy is stored energy. And that's stored energy could be due to position or chemical bonds. Okay. So what I want you guys to think about is, like, let's say I had a spring, right? I have a spring and I push down on the spring so it's nice and compressed. Okay, so that the spring gets pushed down, and so now it takes up maybe this much space. Okay, it's being held into a space. And then if I release that spring from its compressed state, it would spring back and turn into kinetic energy. So when you have a spring that is compressed and it's being held down, it has a lot of stored energy that could be converted into kinetic energy once it's released. That's what potential energy is. Same idea, like if you had a mountain and at the very top of the mountain there was a boulder, it's just perched there ready to fall down the mountain. So a boulder perched at the top of a mountain has the potential to fall down and turn into a lot of kinetic energy. Okay, so again, potential energy is just stored energy that's ready to be released in the form of kinetic energy once it is released. Chemical bonds are the same way. If I have like an O bonded to an O, if I break that chemical bond, it's going to release some energy. And that's actually what happens when we eat food. If you guys ever read the back of like a granola bar package or whatever, it'll say like the number of calories you in one serving is 150 calories, for example. Those food calories are literally how much energy you're going to get based on the chemical bonds that are in the food that you eat. So if it says 150 calories, that means you're going to get 150 energy calories out of that food when you break down the food into its specific pieces that our body gets to use. So anyway, that's a little bit of a tangent, but anyway, that's the contrast between kinetic and potential energy. Okay. Another term that you're going to see in this chapter a lot is enthalpy. Okay. Enthalpy, for the sake of AP chemistry, is just another word for heat. Okay. So when you guys say, some questions might ask, what's the change in enthalpy of a certain reaction? If it's asking for change in enthalpy, it's looking for delta H, which is your change in heat. Okay. And then another thing that also means heat is Q. Okay. So if you guys ever see enthalpy or delta H or Q, they all mean the same thing in this chapter, and it means heat. Okay. So this means change in heat. This specifically means heat associated with the reaction. And then enthalpy, again, is another word for heat. Okay. So, all right, let's get into the messy bit. So here comes our first example of how we do this in chemistry. What we see here is a chemical equation, which we're used to by now, I hope. And something that's new to us is this delta H information. Okay. What this information tells us is that when this reaction happens, we have a release of 890 kilojoules of energy per mole of the reaction. Okay. Do you guys notice that negative sign? That means that the heat is being released. This is an exothermic reaction. So that means if you're standing next to this reaction when it happens, you're going to feel some heat coming off of it. Okay. Which in case, actually, yes, this is a combustion reaction, which would make sense because you would see some fire along with it. Okay. If you ever see a chemical reaction that has its delta H also mentioned, that is a thermochemical equation. Okay, a thermochemical equation is going to give you the heat information, along with the chemicals involved in the chemical reaction. Okay, and I do want to point out what this mole reaction means. Okay, so when you guys see mole reaction, what it specifically means is that we're talking about the oh boy, where did I put that piece of notes? It refers to the balance equation as written. Okay, so what I mean by that is that when 1 mole of CH4 reacts with 2 moles of O2 and producing 1 mole of CO2 and 2 moles of H2O, that's how much heat we're going to get out of it. So we're going to get 890 kilojoules of heat out of this reaction. So the mole ratios are what's important here. That's what the mole reaction means. So in these mole ratios, if it happens in these mole ratios, this is the amount of heat that you're going to get out. Okay, so we'll see some examples, and I think this will make more sense as we work through some examples. So here comes the first one. So we've got our chemical equation here. Our goal is to figure out what is the heat of reaction for this chemical equation. So let's take a look. We've got 22.4 grams of this reactant. When it decomposes, it releases 17.2 kilojoules of energy. Really quick, guys, if the heat is being released, would the delta H be positive or negative? What do you think? If the energy is being released, is the delta H going to be positive or negative? I hope you said negative, because it is true. So if something is giving away heat, your delta H is going to be negative because your overall heat of the system is going to be dropping if you're giving away heat energy. Okay, so let's go ahead and calculate our delta H of this reaction. So in this particular case, we should always start by converting our grams to moles. So we have 22.4 grams of our sodium bicarbonate. And turn that into moles using molar mass. This guy has a molar mass of 84.0 0.008. Okay, so now we know how many moles of NaHCO3 reacted. The next thing we got to do is figure out what the ratio is for the amount of heat energy that was released. So according to the reaction, here's our next step. There was 17.2 kilojoules of heat energy released in our 0.266 moles of NaHCO3. And that's going to tell us that for every, so here's our answer here, we've got negative 64.7 kilojoules released per mole of NaHCO3. Okay, so this means that for every mole of NaHCO3 that decomposes, we would get 64.7 kilojoules of heat released. However, this is the next thing I want you guys to notice. In our balanced equation, do you guys notice that there are 2 moles of this reactant in the overall balanced equation? Okay, so if we want our answer in mole reaction, we have to take that 2 mole into account. So here's what we're going to do. We're going to take this answer and we're going to multiply it by 2. Okay, so I'm going to take this answer, multiply it by 2. Again, we're going to multiply it by 2 because there's 2 moles of this reactant in the overall balanced equation. So when we multiply it by 2, we're going to get negative 129 kilojoules per mole, and that's going to be per mole reaction because in the balanced reaction, there are 2 moles of this compound. Okay, so our final answer for this particular question looks like that. Okay, so again, step 1, turn your grams into moles, and then take your energy, divide it by your number of moles, and then finally look at your coefficient, wherever it is for whatever compound that you're working with. For us, it was the NaHCO3, so it was here. And you multiply your answer by that coefficient, and that will give you your heat associated for the reaction per mole reaction. Okay, let's take a look at how else we can use these kind of information. So now that we have this per mole reaction information, we can also figure out some other things. So now it's asking how much heat would be released if so many grams of that reactant decomposed. So same thing, the first step is going to be similar. We're going to take our grams, so 9.45 grams of NaHCO3, 1 mole, NaHCO3, 84.008 grams. And I'm actually not going to stop there. Next thing I'm going to do is I'm going to use this guy, this heat of reaction, as a conversion factor. So in this particular case, the mole reaction particular to the NaHCO3 was 2. Okay, so for every 2 moles of NaHCO3 that decomposes, we know 129 kilojoules of energy are released. Okay, so here we're going to leave this number on top, and then on the bottom, we're going to use the moles that are specified in the reaction for the reactant that we're using. Okay, so in this case, in the mole reaction, there was 2 moles of NaHCO3, and we were starting the problem with NaHCO3, so that's where we get the 2 down here. This is the most common mistake that people will make, is they'll forget to use the coefficient from the balanced equation down here, so make sure you're paying attention to that. So in your calculator, you guys are going to do this number divided by 84.008, and then times by negative 129, hit enter, and then divide by 2, and then you'll get your final answer. And so this is going to tell us negative 7.26 kilojoules. Okay, so again, don't forget, you have to understand what this number means, right? So right now, this tells us that if we start this overall reaction with 9.45 grams of this stuff right here, if we allow that reaction to proceed forward, we will produce this much heat out of that reaction. Okay, so we're going to see 7.26 kilojoules of heat energy released from the reaction if we start with this many grams of our reactant. Okay, so let's look at our next example. Okay, so again, referring to the same overall reaction, we've got 32.7 grams of H2O produced. As always, we got to turn it into moles first. So 18.016 grams. And again, it's asking how much heat is released when the reaction occurs. So let's take a look. So in the overall mole reaction for this, we have 1 mole of H2O. So when this reaction occurs, when 1 mole of H2O is produced, we know that this much heat is going to be released. So it's a 1 ratio. So 1 mole H2O is negative 129 kilojoules of heat energy. Okay, so that is going to be, again, we're just using a different part of the reaction here. We're looking at now the water that's being produced, but we're still using the delta H reaction. So when we crunch that out, we're going to get negative 234 kilojoules. Okay, so that tells us that if our reaction had produced this much water, that means along with that water that was produced, we released 234 kilojoules of heat energy. Okay, the last type of example you guys might see, if you guys noticed so far, we've seen 2 different examples using this. We first looked at how to calculate the delta H of reaction, and then here we looked at specific grams of either reactant or product. And now we're taking a look at a certain amount of heat. So let's say, okay, we released this much heat. What mass of our reactant must have been consumed? So as always, start out with the number that you're given. In this case, the heat was being released, right? So it's going to be negative 405.2 kilojoules. And you guys should know by now, right? Using the rules of dimensional analysis, whatever unit you start with here has to go on the bottom down here. So we're going to use the 129, negative 129 kilojoules on the bottom. And then, and that's per mole reaction. And if you guys notice, they're asking about the NaHCO3. And if you look back up at the balanced equation, we have 2 moles of NaHCO3. So that means we're going to put 2 moles NaHCO3 up here. And then it says what mass. So the next step is to turn that into grams. So 1 mole of NaHCO3 has a molar mass of 84.008 grams. Okay, so when we crunch this out again, you're going to do this number, multiply by 2, hit enter, divide by this number, hit enter, and then multiply by our molar mass of 84. And so our answer here is 528 grams of our sodium bicarbonate. Okay, so what that means is that if this much heat was released by the reaction, that means that this mass of our reactant must have been consumed. So this, like this mass of this stuff had turned into our products in order to produce this much heat in the process. Okay, so you guys have seen some examples. I want you guys to go ahead and pause and try number 1 and 2. However, if you're still feeling iffy, you're not entirely sure what to do next, that's okay. You can just keep going, see me walk through example number 2, or like the try number 1, and then you can pause and try number 2. So I'm going to go ahead and work through these, but you guys go ahead and pause and see if you can try it yourself. Okay, so here comes the solution for try number 1. So in this case, we've got our 25 grams of chlorine. As always, first step is to turn your moles or your grams into moles. From there, we're going to take the ratio of the energy released to the moles of chlorine that we have. So again, this was energy that's released, so it's going to be negative 191.28 divided by our number of moles. So this is going to be our answer in kilojoules of moles of chlorine reacted. However, we want it in kilojoules of mole reaction. So in this case, take a look at the balance equation. If you guys notice, there's 3 moles of chlorine in this overall balance equation. So what we're going to do is we're going to multiply that answer by 3. And that's going to get our answer in kilojoules per mole reaction. So with 3 sig figs, it ends up being negative 1620 kilojoules of mole reaction. Okay, so that's your final answer for question for try number 1, part A. And then let's take a look at part B. So now that we have the kilojoules of mole reaction, we are going to go ahead and use that to answer part B. So for 67.4 grams of aluminum reacting, first step is to turn that into moles. So 1 mole of aluminum is 26.98. And then we're going to use this guy as a conversion factor. So negative 60, 16, 20. And then according to the balanced equation in aluminum, there are 2 moles of aluminum in the balanced equation. Again, I'm getting this 2 from the fact that there's 2 up here. And then once that's crunched out, we can go ahead and get our answer. So it should be negative 2020 kilojoules. Okay, so what that tells us, if we have this many grams of aluminum reacting in this overall equation, we should expect this many grams or kilojoules of energy released when that happens. Okay, and then let's look at part C. For part C, we're looking at the heat released. So negative, again, it's negative because the heat was released. We're going to use the heat as a conversion factor, so negative 1620 kilojoules per mole reaction, and we're looking at the AlCl3. If you guys notice, there's 2 moles of AlCl3 in the balanced equation, so I'm going to use that 2 moles. And because it's asking about mass, I'm going to turn those moles into mass using molar mass. So 1 mole of AlCl3 has a molar mass of 133.33 grams. Okay, so this tells us then if our reaction released this much heat, then that means this much of our aluminum chloride must have been produced in the overall reaction. Okay, all right, let's take a look at you try number 2. If you haven't worked through it yet, go ahead and pause and work through it. Here comes the answers. So in this particular example, we're working with 1.8 grams of ammonia. One mole of ammonia has a molar mass of 17.034 grams. I'm going to use extra sig figs again because we're not at our final answer. And then again, we're going to use the heat. Again, still the heat is being released, so it's going to be negative 4.85. If this ever says absorbed instead of released, it's going to be a positive number, okay? So we're going to have heat that was released per mole, 0.1057 mole of NH3. And then that's going to get us an answer. Boop. Let's see. So negative 45.90 kilojoules. And again, we're not quite done yet because that's per mole of NH3. However, in the balanced equation, we have 2 moles of NH3, if you notice. Okay, so we're going to take this answer, multiply it by 2, and that's going to get us the heat of reaction. So negative 92. I believe we can only have 2 sig figs. Yeah, negative 92 kilojoules per mole reaction ends up being our final answer there. Okay, so now that we have our heat of reaction, we can go ahead and do part B and C. So in this case, we've got our 692 or 629 grams of hydrogen. Turn from moles in, I'm sorry, from mass into moles. And then we're going to use our delta H of reaction as a conversion factor. In our overall balanced equation, we have 3 moles of H2. So for every 3 moles of H2, we know that we release negative 92 kilojoules. And that's going to get us our answer there. So you guys should have gotten, again, with 2 sig figs only, negative 9,600 kilojoules of heat energy released. So this means according to the balanced equation, if we have, oh no, okay. If we have this many grams of hydrogen combust, or I guess react in this overall reaction, we will release this much heat energy when that happens. Okay, and then last step, we have this much heat energy released by this overall reaction. What mass of NH3 must have been produced? Let's go ahead and work it through. So again, it says the heat energy is being released. And we get to use our heat of reaction as a conversion factor. And it is asking about NH3. The balanced equation says there's 2 moles of NH3. And so we're going to use 2 moles NH3 here. And the question was asking what mass must have reacted. So we're going to go moles to mass. Is it 17? Yeah, 17.03 grams. Okay. All right. So when we multiply that out, we get 730 grams of NH3. Again, can you explain what that means? So if this reaction released this much heat energy, that means we must have also produced 730 grams of ammonia. Okay, so that's part one of the notes. Go ahead and take a breather, take like a little 5-minute break, and then go on to the next part of the notes, please.